What's up guys, welcome back to Vanover Machine and Repair, and we're continuing on today's video with the Lucas horizontal boring mill, and we're going to be focusing in on a step-by-step process on how to rebuild an AC motor. Now if you've been with me for a while, you've noticed that I've had other videos on this in the past, and I've actually learned quite a bit from you guys in the comments section, so I thought I'd put together this video on how to properly rebuild an AC motor, whether it's a small or large motor. Any one of you guys watching along should be able to follow a similar process to get successful results. So without further ado, let's jump into step one of rebuilding an AC motor. Now, before we jump into servicing this motor, I think it's important to talk about why we may want to even replace or service an AC motor in the first place. Now, it may seem obvious, but most people aren't even going to consider doing anything with an AC motor unless it's excessively noisy or doesn't work altogether. And in our case, our motor doesn't fit either of those criteria. Our motor was not excessively loud, and it worked more or less without any issues. However, for us, we were working in this area with the gearboxes removed, and it makes more sense to extract this motor, service it now, than have an unplanned breakdown in the future. The other thing that's important to consider is the cost of a new motor compared to rebuilding an existing motor. A lot of the larger motors, especially one of this size, can be very expensive to replace, $5,000 to $10,000 and up. So for us, servicing this motor makes a lot of sense if we can service it correctly. However, if you're working with a smaller motor, a 1, 2, 3, 4, 5 horsepower motor, and the motor itself has a simple mounting arrangement, it may make more sense to replace the motor altogether. Now the good news is AC three-phase motors are relatively available on the market because they're widely used throughout industry. So even though the MSRP of a lot of AC motors can be quite high, you can actually come across new units fairly cost effectively. Where it becomes a little bit more tricky is with a lot of these machine tools like we have here, where the motor housing is atypical, meaning that we can't just bolt up a stock new motor without doing some sort of fabrication to make bracketry. And that's another reason why you may want to rebuild a motor like this, because you can't just bolt up a factory motor. Now with that out of the way, let's talk about the electrical safety we need to approach before we can even begin to remove this motor. Before any work is performed on this machine, or any machine of that matter, we want to come back here and turn off the disconnect or unplug the machine from the wall. I've already gone ahead and turned off the disconnect on this machine, and I'll meet you over at the breaker box so we can turn the breaker off for added safety. Next, we're going to open the breaker box and turn off the breaker for that machine. And if you work in a factory, you may need to do a lockout tag out so no one comes and flips this back. But in our case, I'm the only one back here, so this should be sufficient. Now that our electrical system is disconnected, we can start by working on our motor. And for today's video, we're going to be focusing on this main drive motor on the back of this boring mill, and we're going to go into the junction box on the motor and start to disconnect some of the terminals. I'm going to start by removing this panel to give you guys a little bit of easier window to see what we're doing electrically. We're going to get this electrical panel cover removed by removing these two screws. Now that we have the cover off, we can take a look at the integrity of our wiring. Most three-phase motors are able to be wired in a high voltage or low voltage configuration. I'll put a picture up on the screen of what that looks like. But in layman's terms, basically if you see 3 wires coming in and going to 3 individual wires from the motor, that's going to be a high voltage setup, so a 440 or 480 arrangement. And if you see your 3 wires coming in going to a pair of 2 wires each, that's going to be a low voltage arrangement, which is going to be for a 220 or 240 setup. And before we go ahead and disassemble this wiring to get the motor removed, it's important to either A, make sure you mark the wires so that you put them back in their original orientation, or also have access to a diagram so that way we get this motor wired up correctly. Now in the event that you do wire the motor incorrectly, all you have to do to reverse the direction of the motor is swap any 2 of the 3 incoming leads, and you can easily change the direction of the motor. So I wouldn't overly worry about miswiring this motor or any other 3-phase motor because it can be relatively easily remedied. With our tape off, we can go ahead and remove these wires. Sometimes you'll find that these are attached with wire nuts. Sometimes you'll find that they're bolted together like this. In general, this method here is a little more reliable. Once I got all the wiring disconnected, I like to go for the belts and the pulley next. On some motors, you need to remove the pulley while the motor is currently installed in the machine. And on this motor, we can actually leave the pulley installed when we lift the motor out. Now, we did go ahead and already remove the belts, so I'm not going to be going over that because we removed the gearbox, but it is relatively straightforward. Generally, the motor has some sort of tensioning mechanism that tightens up the belts, so you need to loosen that, and then once that's done, go ahead and remove the belts. And if you can leave the pulley on, that just makes a little bit less work for you, and in this case we can do that, so we're ready to go ahead and lift the motor out. One last thing I want to point out before we extract this motor is this particular motor has some copper tubes going down to the bearing areas on the motor. Now it appears these copper tubes are fastened to the mounting plate, so we don't need to remove them in this case, but if those were to go somewhere else on the machine, you need to make sure those are out of the way. That way you don't break a line. For our uses, we're going to be switching to a sealed bearing anyway, so these lines are not that critical and they will be eliminated, but that's something you need to watch out for. All right, we're ready to lift this motor out, and when it comes to lifting anything heavy, you want to be as safe as possible. Most motors that are heavy have a lifting eye, and that would be the preferred method for lifting. This eye goes through the plate and into the motor, so we've put a 3/4 tin lifting eye there, and we're going to lift from that point. Now this motor does have a surprise up its sleeve that you're going to see once we pull it out, so we'll talk more about that once we get the motor out, and I think you'll enjoy seeing that because it's a little bit less common on these motors. So let's go ahead and get this motor lifted out. Now with the motor removed from the machine, you can see that this motor and plate is about 500 pounds. So you got to be careful with a lot of these bigger motors because they can get pretty heavy. Let's get it over on the bench and start talking through what we're going to do next with this motor. With the motor on the bench, you guys can see that we're working with a little bit of a unique motor here. The first thing that jumps out right away is this device on the back. This is pretty unusual, but what this is a tachometer. Now, to keep things simple, basically all it does is just monitor the RPM of the motor, and in this machine specifically, it uses an interlock to make sure the machine is happy with the RPM so that everything can continue forward. If there's an issue, it prevents the motor from basically surging if it's locked up or there's extra resistance. This is pretty atypical for a motor, and 9 out of 10 or maybe even 20 out of 21 motors you see aren't going to have that, but I thought I'd mention that. The other thing I want to mention is a correction to our wiring discussion earlier. I made a mistake. I was assuming that this was a 9-wire motor, which is also very common, but this is not. This is actually a 12-wire motor. And as we discussed earlier, a 9-wire motor wired in the high voltage setup would be very simple. 3 wires coming in, T1, T2, T3, connecting to 3 wires, L1, L2, L3, and that's it. Very basic. But this actually has 6 wires. And the purpose of that, without getting into too much detail on the coils and what they're trying to do, is it uses 3 wires to start the motor at a lower current, and then it uses the other 3 wires to run the motor. And this 12-wire motor is a little bit more rare than your typical 9-wire, but it basically allows the user to have a little bit more wiring options, whereas a typical 9-wire motor bonds 3 of the wires and kind of limits your options as far as wiring. So that's what kind of makes this thing unique. So probably the motor that you're going to be rebuilding is most likely a 9-wire, and if that's the case, the diagram that I put up would suffice. But in the event you got a 12-wire, it's very simple. You just have 3 additional wires for starting the motor. So with that being said, I want to talk about the nameplate and what we need to be aware of over there. One thing I would advise before you do any rebuilding or testing is to clean up and read the information tag. This tag is kind of like your VIN number or parts diagram. It really tells you everything you need to know about a motor. In this case, as an example, I thought this motor was 25 horsepower based on my specs from Lucas. But it wasn't until I cleaned up the tag and read it that I realized it was a 15 horsepower. It also has great information about the volts, the RPMs, and in general, it's good to know what type of motor you're working with before you start to disassemble or test anything, and this tag should be able to give you all that information. Even on some of the newer motors, some of the tags will tell you the bearing numbers on the end bells, so you can go off those information when you're ordering your parts. So these tags can be really helpful for that type of stuff. We got the motor out of the machine, we cleaned up the tag, we read the info, and we're ready to move on to the next step. And that is testing this motor. Now, a lot of people jump past this step and start tearing it apart, but this is a very crucial step in determining if this motor is worth rebuilding. Now, the first kind of easy thing to test is just a visual inspection. Now, it may seem obvious, and a lot of this stuff is easier to spot when the motor's clean, but I like to do a walk around of the motor and just check for broken castings, end bells, damage, that sort of thing. The first thing that jumps out to me on this is these damaged oil lines. Now, that was from me being too rough, removing the motor, but in our case, we're going to be deleting those lines and going with a sealed bearing, so it shouldn't be an issue. The other thing I like to do is I like to spin the motor and listen to how the motor sounds to see if the bearings sound healthy. So let's take a look at that. Maybe a little hard to hear, but we have 2 problems. The first thing is those bearings sound absolutely terrible. But the worst issue is, look at this. So we have a major problem here. There's something going on wrong in there, and we have a lot of movement in the bearings. Now, hopefully, we didn't spin the bearings on the shaft or the bearing outer housing in the end bells, but we're not going to know until we get in there. But this is very bad. It's a good thing we decided to take a look at this motor, because this is not good at all. What you are looking for when you spin this is obviously no movement here, but also a nice smooth feel with pretty much no sound. And frankly, if you're going to rebuild a motor, you probably didn't pull a motor out that sounds nice anyway, so I would expect some level of grinding or noise if you're down the road of rebuilding a motor. Now that we got our visual inspection out of the way, we're going to move on to doing some testing on the actual coils in the motor themselves. Now, as a generality, if you were pulling this motor out of a machine and electrically it was functioning fine, most likely it's going to be in good shape electrically. But since we have it on the bench, we do want to go ahead and test the windings on the inside of the motor, because sometimes you can have a problem that develops small It doesn't show up right away in usage, but it can be a major problem down the line and cause the motor to burn out prematurely. So we're really going to be focusing on two different ways to test the motor windings. The first being something that everyone probably has access to, and that is using a voltmeter. So let me get in close and show you how to use that. Now, what we're looking for when we're testing these wires is we're really looking to test the resistance value or the impedance of the coil on the inside of the motor. Now, if there is extremely high resistance or a short to ground or just a short in general, there's going to be a problem waiting to happen. So really the easiest way to do this is to take your voltmeter, and you can use any voltmeter, set it to ohms, which is that omega symbol right there, and just come in here and we're going to be looking for a pair of wires that basically reads around 2 ohms. Now the nice thing about doing this is we really don't need to have a wiring diagram. We really can just come in here and test between any wires and really quickly figure out which wires go to each coil. So for example, I'm just going to come in here and touch 2 random wires. And as you can see, we're getting OL, which means it's a high resistance. So those wires are not connected together. So I'm going to keep coming around here and going until I find something that's around 2 ohms. And this one is. So these two are connected together, and we're getting 1.4 ohms. All right, so we'll keep that in the back of our mind. Those two are a pair. Now we'll come around and we'll just test for another pair. So I'm coming between 2 more and we're getting OL. So those aren't a pair. And it looks like these two are a pair. So 1.6 ohms, all right. So as an example, if we did this and we weren't getting a pair anywhere that we're reading somewhere around 2 ohms, that would be a problem. And then our last should be our last pair. There you go, 1.8. So those all seem relatively fine. And it's also a good idea to just check each wire to ground, right? And if there was a short to ground, you would have some resistance. So I'm not going to do every wire, but you can see I'm going from a ground to the wire, and it's open or overload, meaning it's a super high resistance value. Now we're going to move on to the next test, which is a little bit more accurate. The next test we're going to be using a megometer, and just real quick, the difference between your standard voltmeter and a megometer is going to be that this guy is a universal tool, right? It tests voltage, resistance, impedance, several different things, and it does that relatively well. But when this tests resistance, it does that by sending a small current and or voltage through the wires, and it reports back an ohm reading. For the most part, that works out quite well, except for the fact if you have an issue with a winding or a wire that's maybe not initially as obvious. And in this case, this motor is going to be running at 440 volts. So what may pass just fine with a standard ohm test may actually fail under a heavier load. And that's where the megometer comes in play. This megometer is actually going to be putting between 400 and 500 volts basically into the windings and give us a little bit more accurate picture of the insulation condition on the windings. So we're going to do this test very similar to the ohm test. We're going to ground the negative lead of the megometer, and then we're going to come in here and we're going to touch one of the wires. Once we're clipped on, we'll push this button and it's going to start up top and run all the way down to the bottom. As long as every wire comes all the way down to the bottom, we're good to go. So let's give that a shot. We're good on that one. That one's good. And it's basically charging up those coils with more voltage and letting the resistance bleed off and looking for an issue. So all of them are passing with the megometer. That tells me that internally this motor is most likely fine electrically. And that's really good because this motor had a lot of in-play on the shaft. And so practically speaking, that means that that motor could move around and basically possibly damage some of the windings and or coils. And so to know that we're good to go with the megometer, and we also checked it with the voltmeter just in case, we should be 100% fine electrically and be ready to move on to the next step. Now that we got all of our tests done, it's time to move on to disassembling the motor. And when I start to disassemble the motor, the very first thing I do is remove the pulley. So let's get started with that. First step is to come in here and loosen these grub screws, which hold our keyway in place. When you're removing a pulley, you can do it a number of ways. Installing it is probably a little bit more critical than removing it, but the absolute safest and most efficient way to remove a pulley is to use a pulley puller. And especially on these large motors, you need a rather large puller, and these pulleys can be quite stubborn to remove. I would definitely avoid using a hammer and or trying to do any banging on the shaft or pulley itself. If we can get back here and do a nice clean pull back, that's going to keep this pulley undamaged and our shaft undamaged as well. All right, we're going to be using a 15-ton import pulley puller, and this is a rather large unit, but it makes nice quick work of these pulleys. All right, I've reached the end of my stroke, so I need to pull it out and get a spacer in there. It looks like we're close to the end. There she is. Make sure to take note of any accessories or washers during the removal process. In this case, we may or may not be reusing this, but note the direction you take things apart. We'll get these oil lines removed next. And while removing these, your motor may or may not have these oil lines. Basically, the purpose for this is to add oil or grease to the motor bearings. Most of the time it is grease, but occasionally I have seen these lines be used for oil. And in our case, we're going to be switching to sealed bearings, which basically eliminate the need to service this with grease. So that's why we're removing these guys. And while we're down here, I will make one note. If your bearings are greasable, you do want to make sure you're greasing them, and the best way to know how much grease that you have in them is to grease them until the old grease stops coming out dirty and you have clean grease on the removal port. And that's why we have two ports on this motor. One of these lines is for grease in and one of them is for grease out. So the old grease will sort of work its way through the out port, and that's how you would know that you're done greasing the bearings, is you're getting clean grease on the out after you've installed it on the in port. Same thing up here. One of these is a grease install port, and one of these ports is for grease to be expelled, and that is 180 degrees away from this port. One thing to mention, if you're removing your grease lines like we are, we do need to make sure that these grease plug holes are covered. That way we don't have an area for dust and debris to enter in, and that way no one comes in and tries to grease a sealed bearing. Now that all the grease lines are removed, I like to move on to the rear cover. On most motors, this is a sheet metal cover, comes off relatively easy, but on this motor it looks like it's cast iron and pretty heavy duty. Before we do that though, we need to remove the tachometer, which looks like it might be 4 or 5 5/16 bolts. So let's get that taken off. This is a spline shaft, and it looks like there was a female part that fell off as well. And in this case, it looks like it was potentially broken because this doesn't look like it fits on there. But we'll find out more when we remove this fan shroud. Next, we can remove this fan shroud. And these bolts may actually be for the entire end bell. So if they are, that's fine. And this end bill looks like it might be a little heavy. Or a fan shroud. Generally, the fan shroud is one piece and the end bell is another, but on this motor, it may be a one-piece configuration. We're ready to remove the fan shroud, and due to the weight of ours, we're going to be using the crane just to assist. That way, if it's heavy, we can be safe. Just going to use a rubber mallet and some pry bars to kind of help get this end cap off. And based on what I'm seeing, I'm starting to believe this rear fan shroud is actually an end bell. I forgot a screw here. It was covered in grease, or a bolt rather. So we got all the bolts out now. Let's give that a shot. Trying to work each side gently. All right, here she comes. She's going to come off and fall down a little bit, but we got the hoist on her. All right, a couple things. The first thing is now you can get a better idea of our tachometer. So our tachometer comes in here and is supposed to be coupled to this shaft with this coupler. And as you can see, this coupler basically fell out. So this wasn't doing its job, even though it was installed, so we'll need to address that. And it's kind of hard to see, but there's actually a flat that a set screw went through here, and there was a spacer, and that's completely missing. So it might be in the bottom of the motor fan shroud. But the other point I want to make is look how dirty this is. Now the purpose of this fan is to cool the motor across the fins, and when all these fins are packed with grease, the cooling is dramatically reduced. So just getting this motor cleaned is going to be beneficial. Generally, these fans are plastic. Being careful not to crack your fan. Sometimes it helps if you have two pry bars. See how it comes off nice and easy with even pressure like that. And just wiggle it out. There she is. Now you can see kind of a better design as to how these grease ports work. The excess was up here. They came down with a hose so you could grease it on the top plate, and then this hose comes down over here to the bearing area. And you get an idea, just for you guys here, the level of schmoo that is caked in here from chips and grime and grease that shoots out. So in reality, using a sealed bearing is going to mitigate that. And most likely when we pull this motor apart, we're going to find more of this on the inside, which really isn't ideal. So the next step is to go ahead and take this keyway out back here. For these keyways, I always like to come in here with my soft jaw pliers and try to grab on and lift up. You want to be careful not to damage the area around where the keyway's at. In this case, kind of looks like this is a Woodruff key, and it is. So we'll set that aside so we don't lose it. Next, we're going to remove the end bell, and I like to do the back one first, usually because I'm in the back removing the fan shroud. So usually there are several bolts in the back. Now between assembly and disassembly, assembly is a little more critical. We still want to be careful, but we're not too worried about damaging the bearings because we're replacing them. With the bolts out, what I like to do is go around the edge and gently tap on this end bell and free it. At this point, pretty much all that holding this on is the bearing fit on the outside of the bearing. And it is a press fit, but it's a very mild press fit. So usually I can come over here to these fins and tap on that very gingerly and try to work it as evenly as I can so that we can pop it off. And I like to move to a different fin each time that I'm tapping on, so that way I'm sort of spreading out any minor mushrooming. I do see on here we have a couple screws, so we're going to take these out. Sometimes there's a cap on the back that holds that bearing in its place. So we'll try to remove those and see where we're at. Some motors have those, some do not. And without taking it apart, it's hard to say if that's what this is. This motor appears to be sealed, which is good. However, the grease and dirt we're going to see is going to be as a result of the bearing. I don't want to bring the whole thing out, so I'm just going to tap it. I got my finger here so it doesn't come off the end. You can see we have all this grease that just fell out of this motor, so that's definitely not ideal. But like I said, I have seen much, much worse. So what we're after here is this bearing. We're going to extract that bearing, and then once we're done, we'll pull this rotor all the way out. Now we're going to remove this bearing, and we're going to use a posi lock puller. No brand affiliation here, but I really do like these pullers. They can be used for bearings, pulleys, all sorts of things. And to be honest, we don't need to be too particular about pulling this in the correct manner in terms of damage, because we're going to be getting a new bearing. All we really are cared about is preserving the shaft. So if you had to only do the proper procedure for one, it would definitely be the install. The removal of the bearings, it's a little less critical, but pulling it with a puller versus tapping it with a hammer or using a pry bar is the safest way to remove it, so that's what we're going to be doing. Now in our case, we do have this little nub here, so I'm going to put a socket over that so we don't risk damaging it. Shouldn't really be a lot of force on this bearing. The reason why I like this puller is this cage holds these arms together. So these are a little more pricey, but they're really nice if you're using them frequently. And then we'll pull this guy off. This bearing actually looks not too bad. There's definitely some play in it, but not the type of play that we were experiencing on the front. We're going to get the crane out, and we're going to get some assistance on this rotor, and then we'll go ahead and slide it out. All right, we got our hoist over here. Your motor may be a little smaller, so you may not need this, but for us, we have it just to kind of help assist. Now, the main thing you want to keep in mind when you're removing this rotor is we want to try to avoid dragging it along the bottom of the windings. Some motors that's going to be easier to do than others. If you have two people, it kind of makes this a little bit easier, but in our case, we do have our hoist. So we're just going to put a little bit of upward pressure on this so when we pull out with one person here, we're not dragging it along the bottom. And look at that, we can pull that out without dragging it. With the rotor out, we can now work on the front end bell. Just 4 screws, very similar to the rear. Definitely have some dirtiness in there. With our end bell removed, we're going to move the retaining cap for the bearing with these 2 screws. And the bearing should be pressed into the housing with a mild press fit. If the bearing on your motor falls out, that's a sign that the housing itself is worn, so the bearing would have spun inside the housing. So in this case, it seems like ours is fine. I'm going to tap it out the back, and it should kind of fall out. Now that we got our motor torn down completely, let's talk about each of the parts and some of the issues with each. So with the front end bell here, this end bell is going to be completely fine. That bearing had a sufficient press fit, and overall there's really no damage with this part. The main thing that's obvious is we have a lot of grease in here, and that's not good. So we're going to get this cleaned up, and this part should be fine. Now in terms of our motor body here, same thing applies. We have some oil dripping out. Seems like it could be ATF or some sort of oil. That's not good. The inside of this is caked on with grease. But other than that, there's no moving parts in here. And so this is going to be fine once we get it cleaned up. Now, like we talked about before with testing for a short, if for some reason these wires got damaged or the varnish was removed, one of those wires could short, kind of causing this housing to be bad. But since we already tested it, we know that's the case, that this motor housing / windings are in good shape. So again, this is going to be cleaned up and this housing will be fine. Now, the main issue with this, which you cannot see, is that this inner portion of the bearing is worn, and we'll get to how that happened here in a minute. But both of these bearings are going to get replaced, and that'll be completely remedied. Now, on to our rotor. Now, this rotor is bad, and let me explain. Obviously, being caked in grease is not good. The reason that's problematic is this part spins, and so with all this grease on here, that's going to be increased resistance and overall slow down the motor, and we want to make sure all of that is cleaned and addressed. That's another main benefit for why going to a sealed bearing is helpful. Greased bearings do work well, but if they're over-greased or over time the seals come apart, this is the result of that. Switching to a sealed bearing means we don't have to grease it, which means we don't have to worry about over-greasing it, and that also means that this should never become a problem. Now, here's where our real problem lies. Take a look at our bearing journal here. Now, this may not be inherently obvious because this area is rather smooth and looks intentional, but this area is not intentional. So here is our bearing. And this bearing should be a press fit on this shaft. Notice how I can get it on. This is probably undercut here in the front. And look at that. Where the bearing rides, the shaft is actually worn, and it's worn evenly. And so this is extremely problematic. Typically with a motor service, if you catch it in time, you're talking about cleaning the motor and replacing bearings. This motor is beyond that stage. Now, we can fix this, and we will fix this in the video. However, this motor, for most people rebuilding it, would be done right here because this isn't something that you're going to be able to fix with a new set of bearings and a clean motor. With the motor fully disassembled, I'm going to start by getting my bearings ordered. I like to get that as early in the process as possible, just in case these are a little hard to source. That gives my bearing supplier a couple days to get those while we fix the rest of the issues on this motor. While we're waiting on those to come in, we're going to start by getting everything cleaned up. We want to do that first, so that way we're not slinging grease or whatever over our machine when we go to get this fixed. Now, in terms of cleaning the motor, this is a great opportunity for you keyboard warriors to get charged up because we're going to be doing this a little bit controversially. Now, in a commercial motor shop, they have what is called a heated parts steamer, where they place these parts in. They go in and they use heated steam to clean all of this off. The main benefit of that is when the motor comes out, it's completely dry and clean. However, we do not have one of those machines, so what we're going to be doing is power washing each of these parts individually. Now, as much as you guys may not like that, I've done that on several motors and it works extremely well. We do need to be a little bit careful when it comes to power washing the wires because they are varnished. But for most parts, it works very well as long as everything is properly dried. The other thing we're going to do is before we leave for the day, we'll make sure everything is dry and put a light coat of WD-40. That way we're not letting everything to flash rust. As long as you do it properly, it's quite effective and it works really, really well. What you don't want to do is take a fully assembled motor, power wash it, and then all of the water is sitting in the bottom of the motor to rust away. In this case, because we have everything torn down, we'll be able to wash it, clean it, and blow dry everything out before anything has a chance to rust. Now that we got everything clean and the dirty part is over, I'm going to blow everything out with some compressed air. Now that we got our motor washed, we have it over at our larger oven here, and we're going to be using the dryer to get the rest of the water out of there. And this will just ensure that there's no moisture, water, or solvents left inside the motor. Now I can say from experience that I've done many, many motors using just compressed air and a blower, and it works completely fine. So if that's all you have access to, just spend the time and do a very thorough job drying it out, and it'll probably be fine. A lot of this stuff comes down to technique, right? It's not what you're doing, it's how you're doing it. If you're using a pressure washer, but you're using it really aggressive with a really aggressive tip, you're gonna damage the wire. But if you're being careful, you'll be fine. If you're air drying it, but you don't do a good job, you're gonna have problems. But if you're careful and you're tedious, you're gonna be fine. And that's kind of the theme through this whole sort of process here. Take your time, go slow. If you can rebuild the motor effectively, you're going to be low on material cost, a little bit higher on the effort, but it's going to be well worth it in the end, and that's no different here. So in this case, we do have the oven, so we're going to set this to about 200-ish degrees. This oven's really good at controlling its temperature. The temperature is not too critical. We just don't want to get it too hot, and really we're just trying to get it, 50, 60 degrees above ambient, just to help aid in getting any of that other stuff out of there. So with that said, we'll get this shut, and we actually have a program specifically for it. So on ours, let's see, start, we have a motor dry that we set, no time delay. It's gonna ramp up to 200, it'll hold it there for 3 hours, and then ramp down as fast as possible. And that'll just kind of help out with anything left in the motor. So while this is drying, we're gonna go over to our rotor and start getting that cleaned up as well. While we're cleaning this rotor up here, I'm just scraping the grease off ahead of time. I'm gonna let you know that I'm not going to show you cleaning all of these parts. I know you guys love to see the cleaning, so that's why I'm showing you kind of the two dirtiest parts, but this video is gonna be very long. So I'll show you cleaning this rotor, and then everything else I'll clean off camera, and we can focus on our shaft repair. The other thing I will say is that exterior housing with the coils in it is the most important part in terms of being careful while cleaning. Everything else for the most part is one piece, and you can pretty much go hog wild with the pressure washer. You're not really going to damage anything. Be a little bit more careful on that first one, and then after that, be as efficient as you want. Obviously, use common sense, but you can be a little less careful. You've seen in the last clean that I used some of that degreaser. Technically, you shouldn't use that because it can be abrasive. So do as I say, not as I do there. However, I will tell you just from experience, chemicals have a lot to do with time, meaning that's not something that I would squirt on there and walk away from. But if you get it on there and you wipe it off quick, it can do some good work without being too dangerous. But in this case, I will be using that on pretty much all the rest of the parts. And the longer you let that stuff soak, the more effective it is. And it really does do a good job at getting rid of this grease. And so that's where you really just got to use your brain when you're doing some of this stuff, because using a pressure washer can be a bad thing. Using degreaser, definitely not recommended. But if you use your brain and you use common sense and you be careful, you can get good results and do it somewhat efficiently. You just got to be particular about how you go about doing it. All right, we got the rotor cleaned up, turned out really nice. I actually took it over to my solvent tank after I was done with the pressure washer. That's nice because it helps me just get the remaining grease off, and any worry about water or rust goes away when I put it to the solvent tank because we're cleaning it with solvent afterwards. So overall, I want to inspect this shaft and get it over to the lathe to see what we're working with as far as wear on both sides. But before we do that, I'm going to get everything else cleaned up. So I'll get that cleaned up off camera. Several days have elapsed since we got everything cleaned. We have it out here on the table and ready for reassembly. We ended up using the ultrasonic cleaner for the bolts and small hardware, and now everything has had a chance to fully dry out, which is very important for the reassembly process. The next step is to work on this rotor and the damage that we have over here on the shaft. Here's a closer look at our rotor shaft and the wear that we need to fix. Now this bearing here should be a mild press fit on this journal area, but currently it's about 80 thousandths undersized, and that's the part we need to repair. Now when you're repairing a motor shaft like this, there are really a couple different ways to do it. The first way that I think of is you could cut this off, you could bore this out and put a stub shaft on there. That does work. We won't be doing that. The second method is you could turn this down, you could turn up a spacer, press the spacer on, and get your fit that way. We're not going to do that either. The last method, I believe, is the best method for repairing rotors, and that is a weld buildup repair. Now, in terms of the different styles of weld buildup, there's really three different options. You can either stick or TIG this, you could MIG weld it, or you could do a spray welding procedure. Now, after talking with 3 or 4 different motor shops and talking with a mentor of mine, the absolute best way to do this would be to do a TIG or MIG weld repair. In terms of MIG welding the shaft, we can actually get a really good result as long as we do it properly. Traditionally with MIG, you'd want to run as hot as possible on thicker parts so you get really good adhesion. However, when repairing this rotor, you really do want to go in a little bit of an opposite direction and run a little bit colder. The main reason for that is we're trying to keep the metallurgical property of the shaft as close to factory as possible. And we really are not as concerned with the adhesion as we are just really building up this area and maintaining the original hardness and temper of the shaft. So to do that, we run a little bit colder and we really watch our temperatures, and we can still get a good result. But knowing that if we TIG weld this shaft, we can actually be a little bit cleaner on our weld, and we can monitor the temperature input a little bit more precisely, and that's why we're going to go ahead and TIG this repair. So in order to prepare the surface for TIG welding, we're going to come in here and get this on the lathe and just turn down a little bit of this area. Currently this area is burnished or surface hardened from this hardened bearing riding and wearing in this area. So we want to turn some of that away so we can get down to the parent metal so we can have a really good adhesion with our weld. So let's get this chucked up in the lathe between centers so we can get this turned down. We got our rotor set up in the lathe, and we're going to come in here and just clean this up so we have a real nice surface when we weld this. This is not 100% essential. You could sandblast this area, which would be nice because you wouldn't have to remove any material. What we're trying to do is rough this up just a little bit, but more importantly, dig past this hardened area that was burnished by the bearing rotating around, and just create nice clean metal for us to weld that's nice and clean. So we're going to come in there and just cut out, 30, 40 thousandths and call it good. The next step is to get this TIG welded out. We're using our semi-automatic TIG welding process. With the HTP 221, we're running 160 amps, pulse TIG with 1.7 seconds on time at about 60%. Now we're going to come in here and try to lay down as many passes as we can to get this built up. keeping a keen eye on not overheating the part. We're going to start this way and work up to the shoulder, and then we'll take a break and we'll repeat that process until we get everything built up. First pass is done and everything's looking nice and clean. I'm going to take a quick break, give it 5 minutes, and then we'll come back and we'll put our second pass in. By the way this is laying down, I think we'll be able to be good in 2 or 3 passes, and we'll kind of go from there. All right, our second pass is done. We have a nice tie into that corner. Just wire brushing everything, and we'll let it cool for 10 minutes, and we'll come and do what I believe will be the final pass. All right, we're going to do one more pass. I lied. This is filling out nicely, but it's not worth trying to save 10 or 15 minutes and skip adding a little bit extra material. So that's what we're going to do. It's always easy to add more now than to machine this down and find that we have a small void and come back here. So overall, this is checking out at a little bit over 50 millimeters, but we'll take one more pass and finish it up. We got our cover pass done, and I ran a little bit colder just to try to build it up on the last pass. We ended up doing about 7 passes, which is a little bit more than I anticipated, but I'd rather have a little bit more material than not enough. Right now we're finishing about 51, 51 and a half, and we need to come down to 50. So that should give us plenty of material to remove. We're going to wrap this up with a blanket and let it cool overnight and hit it back tomorrow to get this machined. It's the next day, our rotor has cooled off and we're ready to get this machined. Now it's really important when you're machining a rotor to make sure the concentricity is within spec. Now for your typical motor, 0.002 of TIR or runout or less is what the specification is for most motors in general service. And before we installed or welded on this shaft, we were right at 2000s TIR, which was fine. But now that we've welded it, we want to come in here and check to make sure that our shaft hasn't warped and we're still within spec. The measurement that we're going for on this journal is about 50 millimeters plus an interference fit. 50 millimeters in inches is 1 inch, 968 thousandths and 5/10, and we're going to be adding about 6/10 to that for our interference fit. Let me show you the dial indicator and we'll rotate this around and see what our runout is currently. So we're bouncing around, but we're right around 1.5, 2 thousandths, and that's at the end where the pulley's at. That's perfect. That means we didn't really change at all from where we were before, and we're going to be safe to go ahead and get this machined. We got the rotor finished out and machined down to spec. The next step is to get this area polished where the pulley is. Anytime I pull a motor apart, I always clean this up. It just helps with reinstallation of that pulley. I'm going to go ahead and do that real quick, and then we'll meet you back at the bench to get this guy reassembled. We're ready to get our motor reassembled, and for the most part, reassembling an AC motor is pretty straightforward. There's really two things that you need to keep an eye out for, and the first one is cleanliness. Now, we went ahead and washed all of these components individually, but you want to make sure when you're rebuilding your AC motor that you make sure all of those components are fully dry and clean from contamination. The second thing that is super critical is your bearing selection and installation. So for our project, we're going to be using these SKF Explorer bearings, and we're moving away from the shielded units over to these sealed units so we don't have to lubricate this motor. Even more important than choosing a high quality bearing is how we install them. Now, I've seen multiple people use a hammer to install a bearing, and I've done that in the past when I didn't know any better, but that's bad practice. The reason for that is you have a bunch of steel balls that are hardened in here, and they can actually damage the outer races of the bearings. And that over time can cause excessive vibrations and out of balance, and the bearings will prematurely fail. And that's what we would like to avoid. So whenever possible, it's always best to either press a bearing on using some sort of hydraulic press or arbor press, or do some sort of a shrink fit, meaning you can use a bearing warmer to warm these up and slip them on. That way we're not hammering or tapping on hardened material. So that's something you want to be extra careful about. So with that being said, we're going to move right over to our rotor and get these bearings pressed onto our shaft. Make sure you don't forget your back cap if you have one. Ask me how I know that. Then we'll make sure our shaft is clean and our bearing is clean. A lot of motors have a relief step here to help the bearing get started. Come in here and get this second bearing installed. Let's not forget this back cap. And make sure my bearing is wiped down. And I like to install the bearing numbers up, so when you pull out the housing, you're looking at the numbers. You always want to press on the inner race. Perfect. That's a really nice fit. Not too tight, not too loose. Perfect. We're going to get this rotor installed to the housing. Now, ideally, if you have two people, this would be a little easier. It's okay if this rotor touches the windings, you just don't want to drag it. So if you have one person like I do, you want to get it in, set it down, and then kind of pull it from the other side. So once you have it set up, you can reach around the backside and lift up. Kind of slide it in so you're not dragging. All right, we got our rotor in there. We're ready to get the front end bell installed. The only note I want to make is the OD of this bearing is generally a slip fit on the end bell compared to the press fit of the ID. So that should help installing this a little bit easier. And then the hard part here is just kind of aligning up these screws with the end bell. Sometimes you come to screw it in and it'll push this back. So you got to kind of juggle it on and then get these screws started. We'll get everything together loose and then we'll tighten everything at the end. If you're struggling with these screws, one thing I like to do is just screw a piece of threaded rod in, and you can use that to kind of pull this back so you can get these screws started. I'm struggling to get these two screws in, so I'm going to flip the motor around and get the rear end bell on, and that'll kind of help push the shaft this way. I'm going to leave my threaded rod in, and that keeps it aligned. I'm just trying to gently work this. It's tempting to want to grab a hammer, but it's slowly going. All right, as we're getting close, I'm going to grab my bolts again for the back one, and I can actually see it on the back. So we're about 1/4 inch away. There it is. See if we can catch them on this one on the back. Not all motors have these. It's real gentle. I don't want to push it. All right, we caught it. All right. Second one, same thing. And as we kind of put this rear end bell on, it's going to force that shaft forward and make the front a little easier. I'm going to spin it around and see if I can use the front. I'm going to see if we can catch these threads in the front now. There, just right there, that little bit of wiggling. We caught the threads on this, so we can take our stud out. And I'm going to repeat this process until I can get these to close up. Now that I got all these bolts started on all sides, I can come in here and very gently tighten these up to kind of help press everything together. If I feel like anything is binding, I'm going to stop and readjust. We don't want to force anything. Now we can get this last bolt started here. Actually, I'm going to switch this for one in the back because I'm OCD and the back one will be covered, but this one will not. All right, the front is fully tight. And I think we're going to be able to, yep, pretty much push that in. Tighten these by hand, nothing too crazy. All right, we got the back tightened up. The last thing we got to do is tighten up this end cap. All right, there we go. Everything is nice and tight. With everything tight, we can check our work. We're looking to see how much in play we have. None. Spin it. Make sure it moves freely. Back and forth play. None. I could set up an indicator to show you, but there isn't any. And obviously, you don't want any noise. Can't hear anything. Completely silent. Perfect. We need to plug these grease holes and then work on getting the back fan shroud. For the plugs, we're just using some plastic NPT plugs. Shouldn't make any difference. And I'm going to block all the holes. I'm not going to show you that. It's pretty redundant. But we're just blocking these to keep the motor sealed and to keep anyone from thinking they need to grease it. And for those who are curious, I'll show you. Tenths have run out. And that noise is the indicator. If I take it off, nothing. Put it back on, you can hear it drag. So, job well done. We're actually going to get this motor painted because I need to paint the back half and the fan shroud separately. So we'll get the motor painted and then we'll get the rear fan shroud assembled. Well, I'm choosing this color for you guys. I normally wouldn't paint a motor this color, but I know it'll make it a little bit more interesting. With the motor painted, we can now get our rear fan installed, but before we do that, we need to come in here and install our repaired pickup for our RPM motor. Went ahead and just made a new one off camera out of steel. This old brass one is actually cracked, and it's just not going to work out too well. So this is real simple. We'll just get this in here. It's a slip fit, and there's just a set screw that holds it in. Let's get our Woodruff key installed here for our fan. I'm going to press that down so I'm not tapping on the bearing too much. And now our fan can slide on. Always like to spin the fan, make sure it's not hitting anything. All right, looks good. Now we can slide on our motor rear fan cover. Get our bolts started. Then we'll use our ratchet to just gently snug these bolts up. We're ready to install the pulley on our motor shaft, and this is an area where it's easy to make a mistake. Generally, a pulley is designed to be a slip fit, but through corrosion of the shaft and different operators removing it and installing it, you generally have some form of galling on the shaft or pulley, and it becomes a press fit. So in order to mitigate that, I like to clean up the shaft with some emery cloth on the lathe. If you don't put this in a lathe, you can kind of do it by hand. And then the pro tip is to take the pulley and clean that inner bore out with a flap wheel, and then put it in an oven for 30 minutes to an hour at 300 degrees. That will expand the cast iron pulley and allow us to be able to just slide it on here, and then it'll kind of shrink down a little bit. What we want to avoid doing is beating the pulley on with a hammer, because then we can cause some of that premature damage to the bearings that we talked about earlier. So while that pulley is warming up in the oven, we'll go ahead and get this keyway installed. On this keyway, it has a little ramp on the front. That's designed to go forward, so that way when you're taking it out, it's a press fit. You can get something in there and pop it up. Make sure our keyway sits down there nice, and instead of tapping it down, we'll take our smooth jaw pliers and make sure it's seated fully. And then we'll move on to the next step while our pulley is warming up and get this mounted to our plate. All right, let's go ahead and set our spacers down and get our motor spun around and into position. I'm going to get the 2 back bolts started because they're off the table, and once that's done, we'll flip it 180 and get the 2 front bolts. All right, we just pulled our pulley out of the oven, and let's see if we can slip it on here. There she is. A little hot, but that's all right. Let's put our set screws in. One set screw is to hold the keyway down. The other is just to keep the first set screw from backing out. Our bench assembly is complete. Now we're going to get this installed in the machine. This motor needs to come in at an angle, so we're going to spin it around and we're going to ratchet it up. All right, well, I've got the motor hung up here. I'm going to come down there and just install the electrical box and redo all the connections that we marked when we first started. Then we'll finish getting the motor dropped down and we should be good to go. Our motor is installed and wired up. We have our tension bars a little bit loose. We're waiting to get our belts and our gearbox in there, and then we'll set the tension. But I want to show you how the motor sounds, and then we should be finished. Nice and quiet. Couldn't be happier. Well guys, that wraps it up for rebuilding and servicing this 15 horsepower motor in the horizontal boring mill. I tried to be as thorough and proper as possible for those of you who are following along rebuilding your own AC motors, but I'm sure if I missed anything or made a mistake, you'll correct me down below in the comments. If you guys like more videos like this, check out my playlist, Rebuilding This Lucas 441B, or other videos on our channel. And until next time, we'll see you in the next one.